Okay. So here's the next big thing, and that's energy. So here's the nebulous thing about energy, is that I can stand at the door and watch you all walk in, and I can get an idea of how much energy that you have, okay? So Cohen walks in like, oh, so tired, had Scholar's Bowl, not feeling well, she's like, okay, all right. It's gonna be a low energy day for Cohen, okay? Danny walks in, hi, Mr. Burkamp, how are you? Hair's kind of bouncing, it's like, oh, Danny's a high energy day, okay? Will's steady Eddie, okay?
Oh, yeah.
In all the years that I've taught Will's energy level has fluctuated about 0.1%, okay? Literally, there's this baseline energy level of Will Stanley, and it's just like steady Eddie, okay?
Sounds about right.
No fluctuations at all. So, and you all understand the concept of energy, and you talk about politics and world politics, and there's nations have energy policies in terms of how do we get the energy, how do we produce it, how do we store it, how do we transmit it. But if I said, okay, but what is the definition of energy? And if I said, okay, and don't do this, but I said, okay, get out a piece of paper, write down a definition of energy. Preston, what would you say?
I have an answer.
You have an answer?
Yes.
Go Stanley.
E equals MC squared.
No, that's an equation.
That's the equation.
I want a
okay.
definition.
That is my definition.
E equals MC squared.
Yep.
No.
Okay.
It's an example. Let me throw you a bone. So, from a physics perspective, energy is the capacity to do work. Okay? Now, if you think about it, that makes sense. Saturday morning, 6 o'clock, Mom knocks on the bedroom door, says, hey, we got company coming over, Aunt Martha's going to be showing up, the house is a disaster, I need you to vacuum the floor. Cool. Your mom, I don't have the energy to do it. So from a physics perspective, you're saying, I don't have the capacity to do work. I do not have the capacity to hold the handle on the vacuum cleaner and push it across a distance. I do not have the capacity to do work. Okay? That's what you're saying. When you buy gasoline, fundamentally, what are you buying?
Energy.
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 Okay? And that energy, that gasoline, has the capacity to do work. Now, why don't you put water in your gas tank?
Does not have energy.
Does not have the capacity to do work. There's no energy in it. Okay? Water's at the bottom of the energy well. Okay? That's it. So that's a broad classification of energy. So what we're going to look at with energy is two broad types of energy, potential and kinetic. So potential energy can take on a whole bunch of different forms. Like you can have UG, okay? So UG is gravitational potential energy, and this is where work and energy are two sides of the same coin. So if I take this block, and let's say it's simple, and let's say it has a mass of 1 kilogram, and I lift it up to a height of 1 meter, I did work. Okay, cool. And I would take 1 kilogram times 9.8 meters per second times 1 meter, and I would get 9.8 joules. Okay, I did 9.8 joules of work. Well, by doing that, I also stored 9.8 joules of potential energy. Okay, so I can't store the potential energy of gravitational potential energy unless I do work, unless I take that block and I lift it up. So you can also have energy stored in springs, which is us, okay? And that's going to be 1/2 kx squared. We'll spend an entire day talking about that. K is what's known as the spring constant. X is how far you compressed spring. So let's say that I've got this little penguin toy that shoots out a death laser. So if I push this in, I just did work, okay? I exerted a force over the distance. I stored energy because I pressed that spring in. Now, I push this button and it goes flying out. So the energy that I stored in the spring, which Mother Nature doesn't like, Mother Nature doesn't like the potential energy side of that story. Mother Nature likes the kinetic energy side of that story. So that potential energy then gets transferred into kinetic energy. So then you can also have OOE, which we'll talk about later, like in the spring. And that's just K, Q1, Q2 over distance squared. This is when you have charged particles, okay? Like you have two charged balloons and they're negatively charged and they don't want to be near each other. And it's like, oh, hey, how much potential energy do you have in terms of charge? So the ones we're going to worry about most are UG and US. Now, the kinetic energy comes from the Greek word kinesis, which means in motion. So we're going to have two types. We're going to have translational kinetic energy, which is 1/2 mv squared, and then we're going to have rotational kinetic energy, which is 1/2 I omega squared. Okay? So, if you look at this in terms of units, and Will had even brought up E equals mc squared. Okay, so that's Einstein's famous equation that says if you can convert mass into energy, like in a nuclear reaction, like for example, our sun is the perfect example of this. Our sun is converting hydrogen into helium. And it does it very well, and it's been doing it for about 5 billion years, and it's going to do it for about another 5 billion years, give or take about 10 minutes. And that's what allows us to have energy. So this is mass, and that's kilograms, and that's the speed of light, which is meters per second, and that's going to get squared. So you get kilograms meters squared over second squared, and that leads to the next question is like, well, what's that? Well, if you look at, say, kinetic energy is mass times velocity squared. We don't worry about the 1/2 in terms of the units. Well, that's kilograms meters squared over second squared. Okay, cool. You have rotational kinetic energy. What are the units for I?
Kilogram meter squared.
Kilograms meters squared. Omega is in what?
Radians per
Radians
second.
per second, but that's going to get squared, so that gets you over a second squared. Okay? You have UG, right? Which is mgh. So that's kilograms meters per second squared times meters, which oddly enough gets you kilograms meters squared per second squared. Energy of a spring, we'll deal with that later, you get the same thing. But no matter what, these are all measured in joules. Okay? Whether it's potential energy, kinetic energy, doesn't make any difference. So Will had brought up Einstein's equation, E equals mc squared. To a certain extent, Einstein had a bit of a head start because he couldn't say E equals mc. Why couldn't he say that?
Because the units wouldn't work out.
Yeah, if you took mass times the speed of light, what would you get?
Kilograms
meters per second.
meters
You
per
get
second.
momentum, right?
Meters per second.
So all the
Energy,
physicists
the more
in
it
the world
goes.
would go, whoa, ow, this is bad.
This is
You can't say energy
Bad.
equals momentum, okay? And you can't say, oh, I think it's mc cubed, okay? Can't do that either because the units don't work out. But what he did, in terms of the genius, is that he figured out there was nothing in front of that. There was no 1/2, there was no 1/3, there was no coefficient in front of it. It's just, O equals mc squared. So if you look at generational challenges, let me give you a quick history lesson in terms of what I've experienced. So my dad was born in 1927, and what was now Outlet Cheney Lake. And when Dad was growing up, if they wanted to come into Wichita, number one, 21st Street was a set of wagon ruts. Okay, that's all 21st Street was literally a set of wagon ruts. And they'd have to hook up the horse to the wagon, head out in the morning, come into town, get supplies, whatever they needed, and then go back. And it was literally like a day-long affair to get from Cheney into Wichita, get the supplies, and go back. Okay, so that was Dad's life as a child. But then, by the time Dad passed away in 1997, he saw jet planes developed. He saw international flight happen. He saw man walk on the moon. He saw the space shuttle get developed, where flights to space became routine. So my dad and his generation went from hooking a horse and wagon to come into town to seeing a man walk on the moon. So my dad's generation saw a huge change in transportation and how that changed. I look at my generation. So when I was young, growing up out like Cheney, and this would flip you all out, there was, in terms of communication, you had what was called the party line, okay? So if you've never heard of the party line, and this is how this would work. Number one, the phone was attached to the wall. There was no this is what we call BC, which stands for before cell phones. Yes, there was a time before cell phones.
Nuh-uh.
Shocking as that may be. It's like, oh, what are these dark ages you speak of? And so typically families had one phone, and it was attached to the wall. And you had no privacy because everybody could hear whatever conversations that you had. Even worse, if your family was what was called on the party line, there might be 3 or 4 other houses that shared that line. So what you would have, here was the protocol. So you would pick up the phone, and if somebody else on the party line was talking, you could hear their conversations. Or if you were talking, you had to be aware that Murdo down the street could pick up the phone and listen in on your conversations. So it's like, oh, yeah, it's like, oh, privacy didn't happen. So then,
Myrtle, we throwing hands. I know what you
if
said.
you could afford it, you had a private line. Okay, so then it cost more money to have a private line. So then that would mean you didn't have to at least worry about someone listening in. That was why it was called a private line. The phones at the time were rotary dial. Okay, if you've never seen that, it had like a series of circles. Yep. And you would have something like that. You put your finger in, slide it over here, boom, let go. Okay, and you actually had to remember phone numbers. Okay, I know, shocking as that may be.
Man.
I know. Oh, the injustice of it all. So, I remember I was in 4th grade, growing up at Cheney. Mike Denny, good friend of mine. His family got a push-button phone. And we thought that was the coolest thing in the world. So I remember after school, running to Mike Denny's house to use a push-button phone. Because that was the coolest thing we had ever seen. He also had the very first video game. Anybody know the first video game?
Pong?
Pong. Yeah. He had Pong. I played Pong. And if you don't know what Pong is, it was like table tennis, and you would slide this thing up and down, and it would bounce. Okay, very first video game. It's like that was cool. So when I was in high school doing research papers, like, get this, you had to like go to the library and get books off of the shelf. Okay,
What?
I know, shocking. If you wanted a newspaper article, you had to either physically find the newspaper, or they had something called microfiche, which was the images of the newspaper. And you would grab like 1984. So they would have all of 1984 on reel. And you put it on this reader and you'd crank it, and the images from the newspaper would slide by. And let's say you wanted a story from June 30th, 1984. So you scroll through until you find June 30th, 1984, and then that's how you would find that image, and like, oh, here's the story. Newspapers, magazines, whatever, you had to like physically get a hold of it. Then if you wanted a quote, you had to like write it down. And then to type your research paper, it was with a typewriter. There was no, oh, we'll go back and edit it and print it later. It was boom, 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 just like this. So my generation has seen a transformation in information, okay, and communication. So now, like, you guys don't even have to be able to type. You can just, talk to your phone and go, hey, like this morning, I was getting ready. Said, hey, Alexa, what's the temperature outside? Like, I didn't even have to do anything. Like, hey, what time is it? Hey, what's the capital of Ireland? Whatever, okay? You just have to talk to your phone even now. Like, the other day I asked, like, hey, what's the molar mass of methane? And then gave the answer. So my generation has gone from, hey, let's do rotary dial phones to I just have to talk to my phone, okay? So you guys have access to more information. Now you have AI, which is a whole new realm of possibilities. Now you guys don't even have to think to do an email. You can just go to it and go, hey, type an email about physics or whatever. And it doesn't do bad. Like I've never done it just because I'm too stubborn. But I was on a site and it was just for teachers. It was like Yellow School Bus or something. And I said, hey, develop a lesson for convex lenses. Or no, develop a lab for convex lenses. And that's all I told it. And it did a pretty good lab. I mean, like, it had questions, it had the diagrams, it had the math, it generated the answer key to the questions. It was like, if I was at a pinch, it was like, that's not bad, okay? Not bad. So here's what I think is going to challenge your generation. Your generation is going to be challenged by energy. Because unfortunately, AI, Bitcoin, all these search engines, storing all this information on YouTube, is sucking up a tremendous amount of energy, okay? A tremendous amount of energy. Like to run AI, I don't remember the exact numbers, but to run like one big AI bank of computers took up more energy than it was a country in South America.
Argentina.
Like the entire year.
Yeah.
Okay. It was just stunning amount of energy. Dang. And so your challenge is going to be, how do you produce that energy? Because if you don't have it, we're kind of screwed. Like imagine, I even look at this room. Something happens to the grid. I can't teach in this room. I don't have any windows, okay? I couldn't. It isn't like I have an outside window. It's like, oh, well, still sunlight would come in. This thing would be a tomb, okay? My television, my computer, okay? I'd have a hard time teaching. You look at communication, you look at banking, you look at the internet. So many things are powered by the grid. And the information highway and information stored in the cloud. It isn't physically stored on computers anymore. How would you access that information then? And so you look at levels of carbon dioxide. Last year, 2023, was yet again the hottest average temperature worldwide ever recorded in modern times. Carbon dioxide levels, they just came out and said the carbon dioxide levels are, instead of leveling off like we tried to do, they just keep climbing. And so there's this direct correlation between, and everybody goes, oh, climate change is real. Okay, that's your opinion. That's cool. You can have that opinion. But if you look at carbon dioxide levels, it's doing this. If you look at global temperatures, it's doing this. Oh, might there be a correlation? I don't know. So the question is that, and everybody says, like, where can't you study this? What's your biggest fear? Here's my biggest fear. is that there's a current that runs between North America and Europe. And it carries warm water like a conveyor belt from the equator up into the northern parts of the Atlantic. Okay? It's got this big, long thing. Here's the short version. It's current. It carries warm water up. And it works based upon a temperature difference. Okay? It has to exist. It's a big convection current. It works upon a temperature gradient. And if you don't have a temperature gradient, that current stops. And if the current stops, then Northern Europe, instead of having this vast river of warm water that gets carried up there to mediate its climate, they're basically going to turn into an ice block because of the fact they're not going to have that up there. So about 2 weeks ago, a group of scientists sent a letter to Northern European countries, Norway, Sweden, Denmark, basically saying this current has slowed down to the point that we think it might stop. And if it stops, you can't start it up again. So, and I hope the model's wrong. For your sake of your kids, for the sake of your grandkids, I hope the computer models are wrong. I do. In my heart of hearts, it's like, maybe this isn't as bad as they think. But so far it hasn't, okay? And so that's what you guys are going to be tasked with. You can't go back to the Stone Age. It's like, well, we just won't have electricity. No, okay? Not an option. So that's why everyone says, well, why should you do the solar panels? It's like, the beauty of the solar panels is that, number one, you don't use water, okay? Traditional generations of electricity, you heat water, it spins a turbine, you generate electricity, you ship it a long way, and I can make toast, okay? Because any electricity generation story ends with, I need to be able to make toast, okay? So it's highly inefficient because you got to heat up all the water, and we'll go through all the calculations later. Takes a tremendous amount of energy. There you go. Well, or I can have solar panels that sit right out here, and I ship the electricity 100 yards, and I can make toast, okay? And you don't lose the electricity in that process. Now, here's the knock on solar. Everybody knows the knock on solar. It's like, well, what do you do at night? What do you do when a cloud comes over? And that is because the grid has to have what's called a carrying capacity. And so you have to have a base load. So is solar the absolute end all? No. But you tie solar, you tie wind with grid-sized batteries that can mediate. It's like, oh, a cloud comes over for an hour. So let's say it gets cloudy for the next 10 minutes. Cool. Okay, great. Then you have basically a storage capacity that says, okay, hey, we're losing the capacity from the solar array, then we're going to have a battery that will make up that difference. And that's where I think you're going to see a lot of change. So there's been a tremendous amount of money invested into battery research. There's lithium ions, there's solid state batteries using iron, sulfur. One cool system, and it's very efficient. So it's an automated crane, and it takes big concrete blocks, okay? So they basically, hey, a batch plant is making concrete, they have some left over, they make these big concrete blocks. So what would happen during the day, like you have excess electricity from solar, wind, whatever, what this would do is it would lift up those blocks and it would store it as potential energy. Then at night, you reverse the process. The crane grabs a hold of the blocks and lowers it back down. And then as it lowers it, you're reversing that process and you're changing it into energy. So instead of having like a lithium ion battery to store energy, you're storing
concrete,
gravitational potential energy. And it's actually more efficient than batteries are. So that's...
your mechanical energy, if you gear that up properly, you could get a ton of energy out of one of those.
Yes, absolutely. And it's more efficient than batteries. You lose less in the transfer of energy from one type to the other. Okay, now speaking of transfers of energy from one type to the other, so give the Colt, go and give that a spin.
Spin to over here?
Over here? Okay.
Concrete blocks.
So here I've got this steel block, okay? And I'm going to lift it up over here. Now, when I do this, am I doing work?
Yes.
Yeah.
Yes. Why?
You're exerting a
Lifting.
force over a distance.
It's going to force over distance. I am storing UG. Okay. Now, if I hold this up right here underneath my chin, the way, and I'm going to let go of this. Okay. So I got it right here. Now, why do I know it's not going to come back and hit me in the chin?
Because a little bit of energy is lost.
A little
When it
bit of
swings.
energy is lost. Even if there was no energy lost, would it hit me in the chin?
No.
No.
It would give you a little tap.
Yeah, at
Does
best
it-
it might give me just a little bit of
A brush.
okay?
It would go
didn't
back
shave
to
this
where
morning.
where
might
you
kiss the whiskers.
originally let go.
But so all this is a transfer of energy from one type to the other. So when I hold it up here, you can think of it as like a jar. So when I hold this up here, the jar is full of gravitational potential energy. When I let go of it, what happens to that gravitational potential energy? It changes into
Kinetic.
kinetic energy. So as that changes into kinetic energy, and it keeps going back and forth and back and forth, eventually what's that going to do?
Stop.
It's going to stop. Now, did we lose that energy?
No, it just went elsewhere.
Yes. So one of the great laws that exists is law of conservation of energy, which means that all energy does is change its form. So when that's going through the air, it's colliding with nitrogen and oxygen molecules. It's generating a certain amount of frictional heat. If you listen, you can hear that string vibrate up against the clip in the ceiling. We're losing some energy to sound. So I don't lose the energy. All that happens is that energy just changes form. So this is kind of the cool thing is like, I've been teaching in this room for almost 30 years. And there's been a lot of energy in this room, some caused by tears, some caused by joy, okay? But
Mostly
all of
tears.
that energy still exists. So if you've ever seen the movie, anybody seen the movie Monsters, Inc.?
Yeah.
Yeah.
Yeah, what happens?
It stores the sound of screams as energy.
Yes, okay? So the kids scream, ah! They store the energy, there you go. So somebody who was really bored did the math, and if you could scream, ah, like that for like 8 hours, and harness that energy, you can make a pot of coffee. So, like I said, somebody had to be really bored to make that discussion. Now, here's the story.
Or
So when I hold this up, it has gravitational potential energy.
1 second.
So as it falls down, it's going to fall to this equilibrium point. So here's my question. If I lifted it up to that same height, if I lifted it just straight up here versus over here on an arc, when it hits the bottom, would there be a difference in the speed of the object? Notice I said speed, not velocity. I said speed. So if I lift it straight up and drop it to that same height that I had over there, would there be a difference in speed?
No,
Why not, Will? Your answer is right.
because it's still following the same distance.
They both have the
Like-
same acceleration.
No, the accelerations are not the
accelerations
same.
are-
Oh,
different.
well.
Oh, the
yeah,
accelerations are not
that.
the same.
Yeah.
This acceleration, that's going to take a lot longer to go like that than it is if I just hold it up and boom, just drop it.
Oh, yeah, right.
Okay? Accelerations are not the same. But here's the story. If you look at UG, and this is a bigger discussion, so come and give that a spin. One of the things we have to decide is kinetic energy, and that we're going to deal with translational kinetic energy for now. We'll deal with rotational kinetic energy later, which is 1/2 mv squared. Is that a scalar quantity or a vector quantity? Cohen, your thoughts?
Velocity is a vector quantity, so I'm going to say it's a vector quantity.
Okay. Everybody agree?
Sure.
Sure.
Dang, rats.
I had a 50-50, and I'm really unlucky.
What if you have negative velocity?
Then that's... Oh, it's
Oh, the
squared.
Oh.
So it goes back to...
Positive.
Yes.
range.
So this is going to be important. So kinetic energy is a scalar quantity, okay? So if you look at what I did in lifting that mass up, right? So when I lifted it up, we had a certain amount of height change, whether I lifted it straight up or whether or not it swung in an arc. So if you like a container analogy, we have two containers. We have UG and we have kinetic energy, okay? So whether I lift it straight up or if I swing it over here in the arc, I have a certain amount of UG, 1 joule, whatever that is, okay? So when I let go of it, whether I drop it straight down or if I have it swing in an arc, I still only start with 1 joule of UG. So if I only start with 1 joule of UG, how much kinetic energy could I have? At the bottom,
1 joule.
1 joule. So if I only start with 1 joule of kinetic of UG, the best I can do is end up with 1 joule of kinetic energy. So here's the only difference. If it's swinging at the bottom, that velocity is going to be like on a tangential arc. If I drop it straight down, the velocity is going to be going that way, okay? But in terms of your kinetic energy, because it's a scalar quantity, is there a difference?
No.
No, because it's 1/2 mv squared. Now, is it possible for that mass as it swings down to have both kinetic energy and potential energy at the same time?
Yes.
Oh. Yeah.
Yes.
Because it just... Because, right, it still has some potential energy left. It's not like it all is immediately converted to kinetic the second it starts moving. Otherwise, it would just, like,
Boom.
yeah, instantaneously.
So
everything would
imagine that there's
instantaneously move,
like
which would be
a
bad.
siphon between these two, okay? There's a siphon. So if that's the case, then as this 1 joule of energy that's in the UG container drops, what happens to the level in the kinetic energy?
It
Goes
goes
up.
up.
Because you're transferring that one to the other. Now, once it gets past the equilibrium point, if it's swinging this way, and starts to go up, what's going to happen to the level in your UG container?
Go up.
It's going to go up, but your kinetic energy container is going to
Go down.
go down. Okay? Now, when it reaches its highest point over there, how much kinetic energy does it have? Do not make this difficult.
Zero.
0, because it's going to stop to change the direction, right? Which would be the same thing as me throwing the penguin up in the air. Throw the penguin up in the air. When it leaves my hand, what type of energy does it have? Kinetic. As it goes up, what happens to the amount of kinetic energy?
It goes
It
down.
goes down.
It goes down. What happens to the amount of UG?
It goes up.
It goes up. Okay. Now, it's funny how things have changed. I never really had to have this discussion with my kids because we lived in Kansas, okay? And that's earthquakes, okay? So we don't have as much as we used to. We used to have them all the time. There was a stretch there. So how are earthquakes an example of energy transformation?
Well,
Oh,
it's
the
and then it
tectonic plates
builds
are
up and then it
Yeah, so
Potential
earthquakes
energy
are caused by
and
what? Potential energy changing into
kinetic.
kinetic energy. So there's a fault line, okay? There's the famous one is the San Andreas fault line out in
California.
California,
San
okay?
Andreas.
So basically, the Pacific plate is sliding north, the North Atlantic plate is sliding west, okay? That builds up tension. So you build up enough tension, so it's like taking this string. So if I pull and pull and pull, eventually what's going to happen?
It'll break. It's gonna snap.
It's going to snap. That's what creates an earthquake, is that you build up so much potential energy that eventually that thing is just going to snap. Okay. Let me see. stop that for a second. I need to hand